So I'm going to go over the rest of the Bell Ringer Study Guide questions. And so the first one says that we've got 10 grams of steam. Now, steam is a little bit different than water. It has a specific heat value of 2.01 joules per gram degrees Celsius. So if you did this using the specific heat of water, because steam is just the gas state of water, that's okay, but I am going to show you the correct way to do this. So it says it absorbs 60 joules of heat, so that's our Q, and our Q is equal to mass, which is 10 grams, times specific heat, which is 2.01 times our temperature change. And that's what we're trying to find, is our temperature change for that problem. So we want to solve for our unknown. So we're going to divide both sides by 10 times 2.01. So we're going to do 60 divided by the product of 10 times 2.01. And that's going to give us our change in temperature. And our change in temperature is going to be 2.99 degrees Celsius. You can check your answers for the 3 true false. 10 should be true, 11 is false, it cannot be created or destroyed, and 12 is true. For 13 through 17, the ones that I would want you to make sure to know would be number 14. Joule is the unit of heat and energy. I would also want you to know that specific heat of a substance is the amount of heat required to raise the temperature of 1 gram by 1 degree Celsius. The other things that have to do with calories being equivalent to joules, we didn't focus on a lot of that, so I'm not too concerned about those. But 14 and 15 you should have a good understanding of. So the first thing I want you to notice in number 18 is that we don't have a chemical equation or a reaction telling us mole-to-mole ratios that are producing this amount of energy. And so when we want to calculate delta H, we are going to take our Q in kilojoules and we're going to divide by our number of moles. So for this one, we have our kilojoules, 413.5 kilojoules, and we have our number of moles, 5 moles. So our delta H, our units, is going to be kilojoules per mole. And when I calculate that out, I get 82.6 kilojoules per mole. Now the same thing works for number 19. Again, we don't have a chemical reaction that is showing us how many moles of each chemical are going to produce this energy. So we're going to calculate our delta H. So we use our Q in kilojoules, which is 1,340 kilojoules, and we divide it by the number of moles we have. So again, our answer is going to have a units of kilojoules per mole. I want you to notice it says produces. So that means energy is going out or exiting. And one thing that we have to remember with that is that that is going to be a negative amount of energy then that is going out. So I'm going to put my negative on there. And when I calculate this, I get 1,979 kilojoules per mole. Now the next two are very similar, just a little bit different. So again, we don't have a balanced chemical equation, so we're going to use Q in kilojoules divided by our moles. But the thing with these problems are that we don't have our moles, we have grams of the material, but we do have our Q in kilojoules for this problem. So the first thing I need to do is I need to find my moles of NaI. So this is where our stoichiometry comes into play. We are going to take our 23.2 grams of NaI and we're going to use the molar mass of it. And the molar mass is about 150 grams. 1 mole of NaI weighs about 150 grams. So we have 0.15 moles of sodium iodide. So now I'm also going to notice it says produces. So that means energy is going out. So my Q is negative. So negative 120 kilojoules of energy is going to be divided by 0.15 moles. And once I calculate that, I get negative 800 kilojoules per mole as my answer for that problem. Now, for the next problem, I want you to notice that we are producing in joules of heat, not kilojoules. And we need our Q in kilojoules to calculate our delta H. So the first thing I'm going to do is I'm going to take that 18,300 joules and I'm going to divide it by 1,000 in order to get 18.3 kilojoules. So now I've got my top part of my equation so that I can solve for this. The next thing I'm going to do is I'm going to notice that I have grams of NaOH. So the next thing I need to do is I need to convert my 14.99 grams of sodium hydroxide. I'm going to convert that into moles of sodium hydroxide. So I've got to look up its molar mass, and it is about 40.01 grams. And so it looks like I've got about 0.37 moles of sodium hydroxide. So now I can take this number, and this goes on the bottom. So now I'm ready to solve for my delta H. So my delta H is equal to 18.3 kilojoules divided by 0.37 moles. And so when I calculate that out, oh, I do want to make sure it's producing. So I'm going to put that negative on these so I don't forget about that. It is producing. So negative 49.5 kilojoules per mole is my unit. And there is my final answer for that last problem here. Now, the problem is a little bit different when we have an equation. This is telling us that if we have 4 moles of iron, we're going to get 1,652 kilojoules of energy. It also tells us that if we have 3 moles of oxygen, we're going to get 1,652 kilojoules of energy. It also tells us that if we have 2 moles of iron oxide, that we're going to get 1,652 kilojoules of energy produced. So the first question wants to know how much energy is released when 4 moles. Well, if I look at my information here, I've got 4 moles. 4 moles is making my equation balanced, produces 1,652 kilojoules of energy. Now, what if I only have 1 mole reacting? Well, 1 mole of iron, I can use that relationship from my balanced equation that 4 moles of iron are going to produce 1,652 kilojoules of energy. So when I solve for that, 1 mole is going to produce 413 kilojoules of energy. What if I have 0.067 moles of iron? I can again use that same relationship that 4 moles of iron are going to produce 1,652 kilojoules of energy. And when I solve for that, I get 27.7 kilojoules of energy are released. So I'm using the information from the balanced equation now to find out how much energy is going to be released. Now the last one on this set is a little bit different. It says 12 grams of iron. Well, we have to remember that this balanced equation here tells us a relationship of moles to energy. So the only way that we can figure this out is we have to get that 12 grams of iron into moles of iron. So I'm going to look up the molar mass of iron, and the molar mass of iron is 55.85 grams. So then I find out that I have 0.21 moles of iron. Now I can go ahead and use the relationship that 4 moles of iron are going to produce 1,652 kilojoules of energy, and I get that 12 grams, my answer, 12 grams would produce 86.73 kilojoules of energy. Okay, so let's talk about potential energy diagrams next. First thing, I want you to remember this right here at 80 kilojoules is the potential energy of the reactants. The activated complex, it looks like has 180 kilojoules. So how did I get the activation energy? Remember, the activation energy is the energy needed to get the reaction going. So it's the energy from the reactants right here up to the activated complex. So what I did was I took 180 minus the 80 that I started at, and I got that this energy here to get from the reactants up to being activated would be 100 kilojoules of energy. Now, what is the energy of the reaction? So what I want you to remember here is that when we're looking at a PE diagram, the energy of the reaction is the products minus the reactants. Okay, so we're going to look here. Here's our products. Looks like our products have about 160 kilojoules of energy, and our reactants we had identified as 80. So we're going to do 160 minus 80, and we're going to get 80 kilojoules is our delta H of the reaction. So is this exothermic or endothermic? Well, we can see that from when we started to when we ended, we have more energy at the end than at the beginning. So that means that energy had to go into the system. So that would make this endothermic. Let's take a look at this next one. Again, it asks us for the activation energy. So I'm going to start down here at the reactants, and it looks like my reactants have 120 kilojoules of energy, and I want to find out how much energy do I get, how much energy does it take me to get up to the activated complex. And so that's going to be my activation energy, how much energy to get from the reactants up to the top of the hill. So it looks like my activated complex has about 180 kilojoules of energy. So I'm going to do 180 minus 120, and that's going to be about 60 kilojoules of energy is my activation energy. Next, we want to do the energy of the reaction, which, like I said before, our energy of the reaction is going to be our products minus our reactants. So here's my products. Looks like I'm at about 80 kilojoules. We already identified our reactants being at about 120. So 80 minus 120, I want you to notice that we get a negative number here, negative 40 kilojoules. So that right there is an indication that from the reactants to the products, energy went out of the system. We have less energy at the end than when we started with. And so that negative there and the fact that we see we've got less energy at the end than the beginning, that negative there is going to mean that this is exothermic. Energy went out of the system, and so this reaction here that we see in this potential energy diagram is exothermic. So feel free to pause this part and take a look at the answers for these. Explain why delta H for an exothermic reaction always has a negative value. Well, energy is going to be exiting. And so the products have less energy than what we started with. So what I did was I put an example here to show that if my products had 100 kilojoules of energy, which would be less than my reactants having 150, that I would have negative 50 kilojoules of energy for my delta H, which is a negative value. The next one, explain why a measured volume of water is essential in the calorimeter. Well, we need to know the mass of the water in order to calculate the energy. And that kind of leads right into the next problem where it says explain why you need to know the specific heat. Well, if we want to calculate heat energy, we're going to use this equation here. Q equals mass times specific heat times our change in temperature. And so I put a note that in order to calculate Q, you're going to need those three things. And one of those is that you're going to need specific heat. So for the next problem, I like to draw a picture to identify the system, the surroundings, and the universe. So I drew a calorimeter here, and you can see that for my system, that is going to be just the water and the hot metal that is in there, and then even the little container, that portion that the water and the hot metal is in as part of the system. Now the surroundings is going to be the system, so the container here that is holding that water and hot metal, as well as anything that has outside contact with it out here. Okay, and then finally we have the universe is going to be the two pieces both together. Anything around and outside and touching the system, and anything extending out from there. So for the next problem, the first thing that I need to do is I need to take 12 calories and I need to convert it to joules, because it is asking for specific heat in joules per gram degrees Celsius. So there is 1 calorie is equal to 4.184 joules. So when I multiply that to find out how many joules I have, my Q is equal to 50.21 joules. Now I can use the equation that Q equals mass times specific heat times change in temperature to calculate my C. So I'm going to be calculating for my C right here. Now, one thing you'll notice in my setup here is that I did put a negative for my Q because of the fact that it does say it's releasing this energy. And then I can also notice that my temperature change is a -5. So those negatives will cancel out so that my C here is positive, because specific heat can never be negative. So then all I need to do is solve for my C. And so you can see that I would take 50.21 and divide by -12.5. And that would give me a specific heat of 4.0168, don't forget your units, joules per gram degrees Celsius. Take a minute to pause it and write down the answers to 15 and 16, or check your answers for 15 and 16. The key to remember for 15 is that the Q of the water is equal to the Q of the metal. I would definitely take a look at the worksheet called the Law of Conservation of Energy before you do the pretest, where we have to apply and do exactly what they're asking us to do in problem 15. So take a look at that Law of Conservation of Energy worksheet, and definitely at the video that goes over it, so that way you know how to do that one. And then finally, you can cross out 17, 20, and 21 and just focus on 18, 19, and 22. Make sure to pause the video and write down the answers to those. And then, of course, go back to all the videos that do practice problems and do those practice problems, because there are many math problems on the test. And let me know if you have any questions.